Welcome to Science Views from the Valley. I'm your host, Dr. Kelly Kassan. Science Views from the Valley is a monthly program that will explore interesting science topics and how they relate to the San Luis Valley and the Upper Rio Grande region. Today's topic will be about vaccines, in particular, the history of vaccines, how the mammalian immune system works, and how vaccines work with the immune system. I will not be discussing the politics, since I truly believe that politics should stay out of science. My views today will be strictly on what we know scientifically. My views do not necessarily reflect the views of KRZA or any of their staff. To understand how the immune system works, you must understand the difference between antigens and antibodies. Antigens are molecules that can trigger an immune response. Most of the time, these antigen molecules are glycoproteins attached to the cell membrane of pathogenic bacteria or the protein spikes attached to the lipid-based envelope of animal viruses. But antigens can be other protein and lipid molecules, sometimes even those within the individual's body. For example, people with blood type A have red blood cells with A antigens, while those with blood type B have red blood cells with B antigens. If the red blood cells have both A and B antigens, this person has blood type AB. Only those who are blood type O have red blood cells with no antigens at all. These antigens are why you cannot give blood from a type B person to a type A person and vice versa. It is also why a person who is blood type O can only receive blood type O blood, because any blood type antigens would be viewed as foreign by the person's immune system. Thankfully, our immune systems also have the ability to recognize self-antigens, antigens that are normally produced within our bodies, so they do not attack a person's cells. When this ability to recognize self-antigens breaks down, an autoimmune disease develops. In contrast, antibodies are Y-shaped glycoproteins that are produced by the immune system to identify and neutralize antigens. When B lymphocytes, a type of white blood cell, are presented with fragments of destroyed pathogens or other foreign material, they are activated, meaning that these blood cells begin to reproduce rapidly and differentiate into specialized types of B cells, including the plasma B cell that produces the antibodies. This first response is known as the primary immune response. The activated B cell will also differentiate into memory B cells, which initiate an antibody response if the individual has been re-exposed to the same antigen. Another type of memory cell, the less known memory T cell, has a similar function. This response is known as the secondary immune response, and it is more rapid and stronger than the primary immune response. Thus, you must have a first exposure to an antigen in order to develop a speedy immune response to future exposures to that same antigen. Vaccines, which contain antigens, are designed to trigger the primary immune response, which creates the memory B cells that will initiate the secondary immune response if the individual is exposed to the antigens he was vaccinated against. The memory B cells do not produce the antibodies themselves, but they activate the cells that do produce antibodies against that specific antigen. Antibodies against a specific antigen can be produced for decades or even a lifetime, depending on the antigen and how quickly the pathogen can mutate. If the pathogen mutates and changes the molecular structure of the antigen, our immune systems would have to create a new antibody against the mutated antigen. The previous antibodies would no longer bind to the new mutated antigen. Smallpox antibodies, natural or vaccine-based, can last up to 88 years, which is a lifetime for most people. Antibodies produced by exposure to measles and mumps, either natural or vaccine-based, also provide lifelong immunity or close to it. Vaccine-based antibodies for diphtheria, tetanus, also known as lockjaw, and whooping cough last approximately 10 years. How does this compare to the natural immunity from having the disease? Tetanus does not infer natural immunity. A person who has survived tetanus can and have developed the disease again when exposed to the bacteria. Natural immunity against whooping cough, also known as pertussis, only lasts 4 to 20 years. Natural immunity to diphtheria does provide a longer-lasting antibody, though these antibodies usually do not last a lifetime. Natural immunity gained from having chickenpox will prevent a second case of chickenpox for most people, but the virus remains in the body in an inactive state near nerve tissue. The viruses may reactivate in adults, causing the condition shingles. The varicella-zoster vaccine, named for the virus that causes chickenpox, was developed in 1995. So far, the vaccination appears effective for 10 to 20 years. Vaccines are not 100% effective, much like natural immunity is not 100% effective. Some people who have had chickenpox did develop chickenpox later, for example. Effectiveness of either natural immunity or the vaccines depends on the strength of a person's immune system. The immune system's strength depends on genetics, whether the person is a smoker or not, how nutritious the person's diet is, and how high their stress level cortisol level is. Smoking and high cortisol levels are both known to weaken immune systems. Since cortisol is produced during times of physical and emotional stress, finding ways to reduce stress can strengthen a person's immune system. Poor nutrition is also known to weaken the immune system. Genetic mutations can cause either a less robust or a more robust immune system. Think of the infamous bubble boy David Vetter of the 1970s, who had the genetic condition severe combined immunodeficiency, which severely weakened the immune system. Some people, like myself, do not develop symptoms of the bacterial infection strep throat despite being exposed to it. People with mutations in certain genes can be resistant to specific diseases, like typhoid fever, while others who do not have these mutations will be more sensitive and more likely to contract these diseases. So why were vaccines developed? In short, to cut down on the mortality caused by the disease. Vaccines do have risks, but these risks are much less than having the actual disease. To illustrate this, I would like to give you a short history on the invention of vaccines and how they were developed over the decades. Smallpox, an often deadly disease caused by two viruses, variola major, which caused the more severe and deadliest form of smallpox, and variola minor, which caused a milder, less deadly version of smallpox. The mortality rate of smallpox caused by variola major was approximately 30%, while the mortality rate of variola minor was 1%. The earliest known cases of smallpox occurred in 3rd century BC in Egypt. In 18th century Europe, approximately 400,000 people died each year from smallpox. An estimated 500 million people died in the last 100 years of smallpox, including 6 monarchs: Queen Mary II of England, Emperor Joseph I of Austria, King Louis of Spain, Tsar Peter II of Russia, Queen Eleonora of Sweden, and King Louis XV of France. Survivors, like Queen Elizabeth I in 1563, were left with disfiguring scars on their face and skin. Some were left blind. So the pressure was on for physicians to find a way of preventing smallpox. The first method was developed in Asia in the 10th century. This method, called variolation, involved either nasal insufflation, which was blowing powdered scabs from people who suffered from the variola minor variant of smallpox up the nostrils. The other method, more commonly used in Europe, involved making a shallow scratch in the skin and inserting a tiny amount of smallpox matter taken from patients who had a very mild case of smallpox. The success of variolation led to testing the method on 6 volunteer prisoners in the British Newgate prison in 1721. These prisoners were exposed to smallpox several months after being inoculated via variolation, and all 6 survived. In 1972, Queen Caroline of Ansbach, wife of King George II, ordered the inoculation of 5 orphans at St. James Parish, who were then exposed to smallpox a few months after being inoculated. All 5 survived, so Caroline inoculated her eldest son and heir to the throne, Frederick. Later, Catherine the Great of Russia would have her son and nearly 150 members of her court, as well as herself, inoculated against smallpox via variolation. All survived. George Washington ordered the Continental Army to be inoculated against smallpox using variolation in 1775. The success of this inoculation method resulted in a widespread acceptance in larger cities and towns of the United States. Variolation was not without risks. The method involved using live, yet mild viruses. Even though care was taken to only use smallpox matter from those who suffered from the mild form of smallpox, occasionally deaths occurred. One of those deaths was the youngest son of King George III. But the mortality rate from variolation was far lower than that of smallpox, so variolation continued to grow in popularity. But the search was on for a safer method of inoculation. Edward Jenner was an English physician who is credited with creating the first vaccine. During his lifetime, smallpox killed approximately 10% of the population. Several physicians realized that dairy maidens who were infected with cowpox, a zoonotic virus that is carried by cattle and passed to humans, were immune to smallpox. Jenner hypothesized that the pus and the cowpox blisters might protect others from smallpox just as it had protected the dairy maidens. Jenner tested this hypothesis by inoculating an 8-year-old boy that was the son of his gardener. The boy developed a mild fever but no other side effects. The boy was then inoculated with smallpox material 6 weeks later, but did not show any symptoms of smallpox. Subsequent inoculations of Jenner's vaccine resulted in no failures. No person who was given the vaccination contracted smallpox. The success of Jenner's vaccine led to a worldwide vaccination program against smallpox. By the 1970s, the risk of contracting smallpox was so low that many countries ended smallpox vaccinations. The last natural case of smallpox occurred in Bangladesh in 1975. By 1980, the World Health Organization declared the world free of smallpox. The smallpox virus does remain in laboratory vials today. The U.S. Center for Disease Control and Russia's State Research Center of Virology and Biotechnology have samples. But the last known smallpox death was in 1978, when a laboratory accident released the smallpox virus that infected a medical photographer who worked in the office a floor above the laboratory. Louis Pasteur later investigated vaccinations to combat chicken cholera, an often fatal bacterial infection in chickens. By accident, his assistant had injected months-old bacterial cultures into test animals rather than the freshly grown bacterial cultures. The chickens did not die, so Pasteur injected the chickens with fresh bacterial cultures. None of the chickens became sick. Pasteur hypothesized that the old cultures contained weakened bacteria, which produced a milder form of the disease. This hypothesis led to the second generation of vaccines, those that use pathogens that have been weakened. Pasteur would later produce a successful vaccination program for rabies by using a weakened virus. The rabies vaccine was used on 350 people who were bitten by rabid animals. Only one developed rabies. The success of these vaccines led to the development of other vaccines to combat fatal diseases, including diphtheria, measles, mumps, rubella, and polio. Paralytic polio, another viral disease, had a mortality rate of 2 to 5% in children and up to 30% in adults. Survivors would often have mild to severe muscle weakness. Initially, a passive form of immunity was created by purifying the blood plasma of polio survivors to refine the antibodies against the polio virus. This passive form of immunity had an 80% effectiveness. But limited supplies of blood plasma made widespread use expensive and impractical, so medical researchers focused on developing an effective vaccine against polio. 2 vaccine types against polio were developed. The Jonas Salk vaccine involved using inactivated viruses, but this vaccine needed to be injected. The Albert Sabin vaccine used live but weakened viruses, but could be given orally. Sabin's vaccine was found to be 95% effective after 3 doses, and its low cost and ease of giving the vaccine made it the only vaccine used worldwide. Today, due to the small risk of the weakened polio virus reverting to the dangerous form that causes paralytic polio, most industrialized nations have switched to the inactivated polio vaccine, which cannot revert to the dangerous form. The polio vaccines reduced the incidence of the disease dramatically. In 1952, almost 60,000 cases of polio occurred in the U.S. annually. No cases of polio have been recorded in the U.S. since 1979, though the disease remains a danger in Pakistan and Afghanistan. The measles vaccine was developed in 1963. Measles is also caused by a virus and is one of the most contagious diseases known. The transmission rate for measles is 90%, meaning that if 100 unvaccinated people are exposed to the virus through air droplets or direct contact with fluids from an infected person, 90 people will contract the disease. The mortality rate of measles is low. Approximately 1 to 2 out of 1,000 people will die from measles. The biggest danger of measles is the complications. These complications include pneumonia, encephalitis, seizures, deafness, and worst of all, immune system amnesia. 2 studies in 2019 discovered that the measles virus can eliminate 11 to 73% of memory cells, essentially erasing the body's ability to recognize pathogens that have previously infected the individual. The reduction of memory cells means that the antibody-producing cells cannot be activated, making the person vulnerable to reinfection by other pathogens. Studies of U.S., UK, and Denmark children infected with measles before and after the introduction of the measles vaccine found that nearly half of childhood deaths from infections other than measles occurred in those who had previously contracted measles. Restoration of the immune system took 2 to 3 years post-measles infection. Prior to the measles vaccine, approximately 500,000 cases of measles occurred annually in the U.S., with nearly 500 deaths. Since 2000, measles cases in the U.S. range from less than 100 to just under 1,300 per year. So what kind of vaccines are used today? Currently, 9 different types of vaccines are used. Attenuated virus vaccines use a weakened but live virus. These vaccines are used against yellow fever, measles, mumps, rubella, also known as German measles, and typhoid fever. Attenuated virus vaccines provide more robust protection from the illness, but are more dangerous due to the ability of the bacteria or virus to mutate to a disease-causing variant. Another vaccine type uses inactivated viruses that have been killed by chemicals, heat, or radiation. The glycoproteins of the virus are still intact, which allows the vaccinated person to develop antibodies against the disease, but the pathogen is dead and will not reactivate or mutate to cause disease later. As stated previously, the current polio vaccine uses inactivated viruses. Other examples that use inactivated viruses include hepatitis A, rabies, and influenza. Toxoid vaccines are made not from the pathogen, but the inactivated toxins produced by the pathogen. Vaccines that use toxoid compounds to prevent future disease are tetanus and diphtheria. Another toxoid vaccine is made from rattlesnake toxins and is used to vaccinate dogs against rattlesnake bites. Conjugate vaccines are used against bacteria that have a polysaccharide outer coat that reduces the ability of a person's immune system to recognize it as a pathogen. Scientists have linked these bacterial outer coats to proteins that do initiate a strong immunological response, in essence, training the body's immune system to recognize the pathogen's outer coat as an antigen. One conjugate vaccine that is currently being used is for serotype B meningococcal disease. Heterotypic vaccines use closely related pathogens of non-human animals, much like Jenner's use of cowpox to immunize against smallpox. The BCG vaccine, used against tuberculosis, is an example of a heterotypic vaccine that is used today. Viral vector vaccines use a different, less harmful virus as a vector to deliver nucleic acids coding for an antigen of a virulent or dangerous pathogen. This type of vaccine has currently been approved for use against Ebola and COVID-19. The COVID-19 vaccines that use this type are the Oxford, AstraZeneca, Sputnik V, Convidencia, and the Johnson & Johnson vaccines. All of these use a modified adenovirus as the vector. The last type of vaccine is also the newest type, the RNA vaccine. This vaccine contains synthetic RNA sequences that code for a particular antigen that will cause an immune response. The RNA is read by the ribosomes of the cells of the person who was vaccinated, and they make the foreign antigen protein that is coded for by the RNA. This triggers the immune system to produce antibodies and memory cells against that antigen. The Pfizer and the Moderna vaccines are examples of RNA vaccines. Because the RNA is read by the ribosomes in the cytoplasm of the cell, the RNA does not integrate into the DNA genome of the cell. So once the RNA is read by the ribosome, it is degraded by the cell's natural processes just like any other RNA. Since the DNA genome is not affected, once the RNA is degraded, no new copies of the RNA is made. Vaccines, as I stated previously, are not without risk. Many have side effects, though most of these side effects are in the forms of fever and fatigue, a normal immunological response to a foreign protein. The purpose behind the development of vaccines was to reduce the risk of mortality or complications from these diseases. Vaccines also do not guarantee 100% prevention from contracting the disease. The effectiveness of a vaccine depends on your body's response to the vaccine, which can vary greatly from person to person, just like a person's immune response to having the disease can vary greatly. Thank you for listening to my discussion on vaccines. I hope you found this topic informative. If you have a question or topic that you would like to hear discussed on the show, send me an email at spiderwomankrza@gmail.com. If you would like to hear my past shows, they are archived on YouTube at Science Views from the Valley, Alamosa, CO. Next month's show will be on October 28th, when I will discuss Thomas Edison and Nikola Tesla. I would like to thank everyone here at KRZA for their help in developing this show.